Okay, today we're going to look at section 7.3, which is combination. Now, permutations, we study permutations, which we use to count the number of ways to generate an ordered list of a given length from a group of objects. An important property of permutation is that order of the list matters. The results of a race, the selection of club officers are examples of this, where the order is important. In other situations, the order is not important. For example, in most card games where a player receives a hand of cards, the order in which the cards are received is irrelevant. In games where a player receives, in fact, players often rearrange the cards in a way that helps them keep the cards organized. So combinations is when order doesn't matter. So in a situation in which the order of a list of objects doesn't matter, the lists are no longer permutations. Instead, we call them combinations. So let's decide whether the following represent permutations or combinations. On Halloween, you give each kid who comes to your door 3 pieces of candy taken randomly from a dish. So this would be a combination. Well, would it? Yeah, the order doesn't matter. They're still getting the same 3 pieces. Your class is going on a field trip, but there are too many people for one vehicle. Your instructor chooses half the class to take the first vehicle. Does it matter the order he picked those students? No. So again, this is combination. Permutations and combinations are certainly related, because they both involve choosing a subset of a large group. So let's explore that connection so that we can figure out how to use what we know about permutations to help us count combinations. We'll give a basic example. How many ways can we select 3 letters from the alphabet group A, B, C, D, E? If the order matters, that number is 5, choose 3, or 60. That's small enough that we can list them all in the table below. So we have them listed here. Now let's look at the list and color code it so that groupings of the same 3 letters get the same color as shown in figure 7.9. So as you can see, after color coding, we see that 60 cells can be seen as 10 groups, colors of 6. That's no coincidence. We've already seen how to compute the number of permutations using the formula n factorial over n minus r factorial. To compute the number of combinations, let's count them another way using the multiplication rule for counting. We do this in 2 steps. Choose 3 letters, pay no attention to orders. Put those letters in order. Number of ways to choose 3 letters from the group of 5 is the number of combinations we're looking for. Let's call that number 5C3. Read the number of combinations of 5 objects taking 3 at a time. We can see from a chart that this is 10, the number of colors used. We can generalize our findings this way. Remember that the number of permutations of n things taken r at a time is n factorial over n minus r factorial. That number is equal to NCR times r factorial. So it must be the case that NCR equals NPR times r factorial. So if we divide both sides of that equation by r factorial, it gives us the formula below. So the number of combinations of n things taken r at a time is equal to n factorial divided by r factorial times n minus r factorial. So this is the difference. If order does not matter, we divide by r factorial as well. So this compute 6CR is 6 factorial over 4 factorial times 6 minus 4 factorial. That gives us 6 factorial over 4 factorial times 2 factorial, which in turn gives us 6 times 5 times 4 factorial over 4 factorial times 2 times 1. 4 factorials cancel out, and I have 30 divided by 2, which is 15. Let's look at some more of these. And let's do number of combinations of 10 people taken 8 at a time. So this is equal to 10 factorial over 8 factorial, 10 minus 8 factorial. 10 factorial over 8 factorial, 2 factorial. 10 times 9 times 8 factorial over 8 factorial times 2 times 1. 8 factorials cancel out. I have 90 over 2, which is 45. And one more here, just basic. Number of combinations, taking 5 things out of 14. So we have 14 factorial over 5 factorial, 14 minus 5 factorial. So we have 14 factorial over 5 factorial, 9 factorial. So 14 times 13 times 12 times 11 times 10 times 9 factorial over 5 times 4 times 3 times 2 times 1 times 9 factorial. 9 factorials cancel out. I know this one is 120. So 14 times 13 times 12 times 11 times 10. That gives me 240,240 divided by 120 should give me 2,002. So let's look at some applications of this. At a charity event with 58 people in attendance, 3 raffle winners were chosen. All received the same prize, so order doesn't matter. How many different groups of 3 winners can we choose? Well, we have 58 people, order doesn't matter. We're choosing 3. 58 over 3 factorial times 58 minus 3 factorial. 58 factorial, sorry. And we have 58 factorial over 3 factorial times 55 factorial. 58 times 57 times 56 times 55 factorial over 3 times 2 times 1 times 55 factorial. 55 factorials cancel out. I know this is 6. 58 times 57 times 56. We have 185,136 divided by 6. Was 30,856. Now, even with this division, notice something. All of our answers have been whole numbers. When you're calculating this, we're calculating the number of ways we can make a combination, number of ways we can arrange things. So our answer should always be whole numbers. If you get a fraction somehow, you made an error and you need to figure out where that error is. Okay, so now we have a sorority with 42 members needs to choose a committee with 4 members, each with equal responsibility. How many committees are possible? Equal responsibility for each member means order does not matter. So we're taking 42 and we're choosing 4. So I have 42 factorial over 4 factorial times 42 minus 4 factorial. 42 factorial over 4 factorial, 38 factorial. We have 42 times 41 times 40 times 39 times 38 factorial for 4 times 3 times 2 times 1 times 38 factorial. 38 factorials cancel each other out. I know this is 24. So we have 42 times 41 times 40 times 39. Gives me a whole lot. Two, 6, 8, 6, 3, 2, 0. Divide that by 24. And I get 111,930 different members, groups, committees. Okay, how many ways are there to choose a hand of 6 cards from a deck with the constraint that 3 are spades, 2 are hearts, and 1 is clubs? Okay. Okay, so first thing we're going to look at is there are 13 cards in each suit. So there are 13 spades. So I have 13 and I'm going to choose 3 and the order doesn't matter. There are also 13 hearts. I'm going to, out of 13, I'm going to take 2. And there are also 13 clubs. I'm choosing 1. So starting here, I have 13 factorial over 3 factorial, 13 minus 3 factorial, which is 13 factorial over 3 factorial times 10 factorial, or 13 times 12 times 11 times 10 factorial over 3 times 2 times 1 times 10 factorial. 10 factorials cross out. I know that's 6. 13 times 12 times 11. 1,716. Divide it by 6. And there's 286 ways to get 3 spades. Okay, now to do the hearts, same process. 13 factorial over 2 factorial, 13 minus 2 factorial, 13 factorial over 2 factorial, 11 factorial, 13 times 12 times 11 factorial over 2 times 1 times 11 factorial. 11 factorials cross out. And I have that 156 over 2. Let me double check that. 13 times 12. Yes, 156. Divided by 2. Oh, 78. And then this one, they have 13 factorial over 1 factorial, 13 minus 1 factorial. 13 factorial over 1 factorial, 12 factorial. 13 times 12 factorial over 1 factorial times 12 factorial. 1 factorial is simply 1. 12 factorials cancel out, and I end up with 13. So I have 286 ways to choose 3 spades, 78 ways to choose 2 hearts, and 13 ways to choose 1 club. So to get my hand here of 6 cards, it's 286 times 78 times 13. Which is 290,004. And that finishes up our combination section.